In December 1942, American shipbuilders delivered the USS Essex to the United States Navy, a magnificent aircraft carrier that had gone from blueprint to battle-ready in just 20 months. British naval commanders, who typically required 4 or 5 years to construct similar vessels, were utterly bewildered. "Impossible," declared Admiral Sir Bruce Fraser upon learning of the American construction timeline. "There must be some mistake in the intelligence." When presented with photographic evidence of the Essex undergoing sea trials, British Admiralty officials reportedly spent hours scrutinizing the images for signs of deception. Admiral Percy Noble, head of the British Naval Mission in Washington, dispatched 3 separate teams to verify the vessel's completion status, convinced there must be some misunderstanding about the carrier's readiness. "Either they've built a hollow shell with non-functioning systems, or they've somehow completely revolutionized naval construction," he wrote in a classified cable to London. What the British didn't realize was that this was just the beginning of an unprecedented industrial achievement. By war's end, America would produce 24 Essex-class fleet carriers, more aircraft carriers than the combined navies of every other nation on Earth had ever built. Today, you will discover how American ingenuity, industrial might, and revolutionary assembly techniques not only perplexed our British allies, but fundamentally changed naval warfare forever. The story begins in the tumultuous days following Pearl Harbor. December 7, 1941 had delivered a devastating blow to American naval power in the Pacific. In a single attack, the Imperial Japanese Navy had crippled the American Pacific Fleet, sinking or severely damaging 18 ships, including 4 battleships. The situation was dire. America faced a determined enemy across the vast Pacific Ocean with a severely depleted naval force. Intelligence reports indicated the Japanese had a decisive advantage: 6 fleet carriers to America's 3 in the Pacific theater. More troubling still were the classified naval intelligence assessments that crossed President Roosevelt's desk in January 1942. These reports, declassified only in 2012, revealed that Japanese shipyards had begun construction on 5 additional fleet carriers, with 2 nearing completion. American naval planners faced a staggering deficit. By mid-1942, they projected Japan would operate twice as many carriers as the United States in the Pacific. The only American carriers under construction, USS Essex and USS Independence, weren't expected to join the fleet until 1944, at the earliest, based on pre-war construction timelines. British naval experts estimated it would take years, perhaps even a decade, for the United States to recover from such losses. "The Americans will be lucky to launch 2 new carriers before 1944, wrote First Sea Lord Sir Dudley Pound in a confidential assessment to Winston Churchill in January 1942. This pessimistic British assessment was understandable. After all, their newest carrier, HMS Indomitable, had taken 57 months from keel-laying to commissioning. The Royal Navy's pride, HMS Illustrious, had required 46 months of meticulous construction at Vickers Armstrong Shipyard. British shipbuilding tradition emphasized craftsmanship over speed, with skilled artisans laboriously constructing each vessel as a unique masterpiece. When Admiral Andrew Cunningham, then serving as First Sea Lord, reviewed American plans to accelerate carrier production, he dismissed them as wishful thinking divorced from shipbuilding reality. As he explained to Churchill, "Building a modern aircraft carrier is not like building a merchant ship. The complexity requires methodical, sequential construction. The Americans simply cannot compress 5 years of work into 2 without sacrificing quality to a dangerous degree." What the British didn't understand was that America had already begun revolutionizing naval construction methods that would shock even our closest allies. In just 24 months, you'll understand how Americans transformed this catastrophic disadvantage into one of the most decisive industrial and military advantages in the history of warfare. The first glimpse of American industrial superiority came with what shipbuilding experts called modular construction, a revolutionary approach that British naval architects had considered but deemed too complex for vessels as sophisticated as aircraft carriers. Traditional shipbuilding required sequential construction, building a vessel from keel to completion in a linear fashion. American engineers, however, had different ideas. At Newport News Shipbuilding in Virginia and other yards across the country, engineers divided each carrier into hundreds of discrete modules, complete sections that could be built simultaneously by different teams in different locations. These prefabricated sections, some weighing up to 250 tons, were then brought together for final assembly. Naval Construction Battalion records, declassified in 1997, reveal the astonishing scale of this innovation. USS Essex was constructed from 217 separate modules, assembled at 5 different facilities before final integration at Newport News. This approach allowed specialized teams to work on identical components across multiple carriers simultaneously. For example, the machinery spaces containing the complex propulsion systems were identical in all Essex-class carriers. Engineer William Barnes, who headed Newport News Propulsion Division, established a dedicated team that did nothing but build these modules. By their 4th iteration, they had reduced construction time from 14 months to just 4.5 months per module. When British naval observer Captain William Davis visited the Newport News facility in March 1942, he reported back, "They are building these ships like automobiles, not vessels. It's unlike anything in our naval tradition." The Americans had fundamentally reimagined shipbuilding, treating massive carriers not as unique craft projects, but as industrial products. Rear Admiral Edward Cochrane, chief of the Bureau of Ships, explained the philosophy to skeptical British observers. "We don't see a carrier as a single ship. We see it as 250 discrete manufacturing problems to be solved in parallel, not in sequence." This approach allowed shipyards to employ specialized teams focused on identical components across multiple vessels. While a British yard might have craftsmen building a single aircraft elevator over 6 months, Newport News had teams that did nothing but build aircraft elevators, becoming so efficient they could complete the same component in just 3 weeks. The specialized teams developed innovations that would have been impossible under traditional construction methods. The flight deck installation team at New York Navy Yard, for instance, developed a technique for pre-stressing the deck armor that reduced installation time by 40% while simultaneously improving protection against armor-piercing bombs. Most shocking to British observers was the American practice of starting construction before final designs were complete. "They're building the forward sections while still finalizing the stern design," noted a bewildered Commander Thomas Langford, Royal Navy Engineering Liaison. "It violates every principle of proper naval construction." Yet this calculated risk, building to preliminary designs while remaining flexible enough to incorporate final specifications later, slashed months from construction timelines. When Commander Langford expressed concern that this approach would lead to structural incompatibilities, American project manager Robert Williams simply laughed. "We build in the tolerance from the beginning," he explained. "Each module is designed with connection points that can accommodate up to 4 inches of dimensional variance. It's actually more forgiving than traditional construction." But this was merely the beginning of American innovation. Guardam essa informação, porque o verdadeiro teste ainda estava por vir. Behind the unprecedented speed of American carrier production stood thousands of ordinary citizens who answered their nation's call with extraordinary dedication. Imagine being Rosie Monroe, a 24-year-old housewife from Michigan who had never seen the ocean, let alone built something that would sail on it. At the Kaiser shipyards in Vancouver, Washington, she learned to operate a welding torch in just 2 weeks. These women are doing work that seasoned shipbuilders claimed required years of apprenticeship, noted British observer Lieutenant Commander Harold Winston in July 1942. Her story, documented in Navy archives, reveals the transformation of American manufacturing. Within 6 months, Rosie had become a welding inspector responsible for certifying work done by dozens of other welders. By war's end, she had personally trained over 200 new welders and helped develop a simplified welding protocol that was adopted across multiple shipyards. Across America, the workforce in shipyards exploded from 8,000 pre-war specialists to over 650,000 men and women, many with no prior experience. Women made up nearly a third of this workforce, shattering every preconception about shipbuilding capabilities. They mastered complex skills with remarkable speed, often outperforming veteran male workers in precision tasks like electrical wiring and instrument installation. Margaret Jenkins, a former elementary school teacher, became one of the top hull inspectors at New York Naval Shipyard, her attention to detail catching flaws that veteran male inspectors had missed. Her division achieved a 98.7% first-time quality pass rate, the highest in the yard's history. Previously undisclosed Navy reports reveal that female quality control teams identified 17% more defects than their male counterparts, dramatically improving vessel reliability. At Bethlehem Steel's Fore River Shipyard in Massachusetts, production manager William Cotter implemented an innovative training program that reduced the learning curve from months to weeks. "We don't have time to train shipbuilders the old way," he explained to skeptical British observers. "So we broke down complex skills into simpler components that could be mastered quickly." This approach allowed former farmhands, school teachers, and office workers to become productive shipyard workers within weeks rather than years. An internal efficiency study from April 1943, recently declassified, showed that workers trained under Cotter's method reached full productivity in an average of 17 days, compared to the 120 days required under traditional apprenticeship systems. The program was so successful that the British Ministry of Labor sent 3 separate delegations to study it, although their recommendations to implement similar approaches in British yards were largely rejected by tradition-bound management. At the New York Naval Shipyard, production operated 24 hours a day, 7 days a week, with 3 complete shifts. Workers routinely exceeded production quotas by 15 to 20%, with some teams pushing to 150% of expected output during critical phases. The USS Intrepid's forward hull section was completed 2 weeks ahead of schedule when the night shift decided to remain on duty through a weekend to show the day shift how it's done. A handwritten note found in Navy archives from Yard Supervisor Thomas McGrath reads, "Have never seen such determination. These people aren't building a ship, they're building victory, and they know it." In Philadelphia Naval Shipyard, a team of 58 electricians, led by former radio repair shop owner Samuel Greenfield, set what was thought to be an impossible record, completing the entire electrical system for USS Bunker Hill in just 47 days, less than half the time allocated in the construction schedule. When asked how they accomplished this feat, Greenfield's response was simple. "We redesigned the installation sequence and worked in teams of 3 instead of the usual pairs. Nothing complicated about it, just American ingenuity." Newly declassified War Production Board records reveal that American shipyards achieved an average of 94% attendance rates despite demanding physical conditions, a level of workforce dedication that astounded British labor officials who struggled with absenteeism in their own yards. When Admiral William Halsey later toured these facilities, he remarked, "When I saw what ordinary Americans were accomplishing here, I knew we couldn't lose this war. If you're impressed by this mobilization, wait until you see what happened when these American workers were paired with revolutionary new technologies." In August 1942, American shipyards unveiled a technological advancement that left British naval architects in disbelief: the application of welding instead of riveting for carrier construction. Declassified Navy documents reveal that this single innovation reduced construction time by 35%. Traditional riveting required drilling thousands of holes, inserting metal rivets, and hammering each one individually, a painstaking process that had changed little since the Victorian era. A single Essex-class carrier required over 1.2 million rivets when built using traditional methods. Each rivet hole had to be precisely drilled, the rivet inserted, and then hammered into place by teams of skilled workers, a process that consumed over 180,000 man-hours per vessel. The labor intensity was staggering. A skilled riveting team could install approximately 250 rivets per day. Simple arithmetic made the challenge clear. At that rate, the riveting work alone would require over 4,800 team days of labor. American engineers, drawing on innovations from the automobile industry, perfected high-speed welding techniques that created stronger bonds with significantly less labor. Electric arc welding, previously considered suitable only for non-critical structures, was perfected by American metallurgists to create joints stronger than the metal being joined. The breakthrough came when Dr. Robert Hopkins at the Naval Research Laboratory developed a new welding rod coating that prevented oxygen contamination during the welding process. This innovation, documented in technical papers declassified in 1972, allowed for deeper penetration welds that eliminated the structural weaknesses that had concerned British engineers. Laboratory tests conducted at the Massachusetts Institute of Technology in June 1942 demonstrated that Hopkins' welded joints could withstand 23% more stress than traditional riveted seams before failing. "I've spent my career building ships according to Admiralty specifications," wrote British Naval Attaché Commander Robert Willingham in a confidential report. "What I witnessed in American yards makes our method seem medieval by comparison." At Newport News Shipbuilding, engineers developed an automated welding machine that could lay down perfectly uniform welds at 5 times the speed of a human welder. The device, nicknamed the lightning bug by yard workers, could complete 20 feet of precision welding in just under 8 minutes, a task that would take a skilled manual welder nearly an hour. More impressively, the machine maintained consistent quality, regardless of environmental conditions or time of day, eliminating the variability inherent in human performance. The British Admiralty initially refused to believe the reported speeds, sending a special technical mission in October 1942 to verify American claims. Their report, marked most secret, confirmed that American welding techniques were indeed revolutionary. "The Americans are achieving in days what would take weeks in our yards, with weld quality that exceeds our best hand-worked riveted joints." But the advantages of welding extended far beyond construction speed. These welded seams were not only faster to create, but produced lighter, stronger vessels that could achieve higher speeds with the same power plants. An Essex-class carrier built with welded construction weighed approximately 820 tons less than an equivalent riveted design, allowing for higher speeds and greater aircraft capacity. Speed trials conducted in January 1943 revealed that USS Essex achieved 33 knots, 2.5 knots faster than design specifications. This unexpected performance boost translated directly to combat capability, allowing American carriers to launch and recover aircraft in higher wind conditions and outrun certain classes of submarines. The welded hull sections also exhibited superior water tightness, a critical factor in combat survivability. Damage control tests conducted on scale models at the David Taylor Model Basin demonstrated that welded compartments maintained integrity under pressures that caused riveted seams to fail. This structural advantage would later save numerous American lives when carriers sustained battle damage in the Pacific. A post-war analysis by the Naval Technical Mission concluded that welded construction improved the survivability of damaged vessels by approximately 37% compared to riveted construction. Guardem essa informação, ela explica tudo o que vem a seguir. In years studying military conflicts, I've found that true superiority often emerges not on the battlefield, but in the factories and shipyards, where innovative thinking transforms the very foundations of warfare. From the perspective of British naval officers who visited American shipyards in 1943, the scene bordered on industrial sorcery. Declassified communications between the British Admiralty and their Washington attachés reveal their astonishment. The Americans have somehow eliminated the most time-consuming aspects of carrier construction, wrote Captain Malcolm Fitzgerald in March 1943. They've reduced a 5-year process to under 2 years without apparent compromise to structural integrity. His detailed report, running to 47 pages, attempted to explain this American miracle to his superiors in London. But his frustration was evident in the concluding paragraph, "I have observed their methods directly, documented their techniques, and still find myself at a loss to fully explain how they are achieving such results. They seem to have reimagined the entire shipbuilding process from first principles. What particularly confounded the British was America's revolutionary approach to managing complex construction projects. While Royal Navy shipbuilders relied on traditional master craftsmen overseeing apprentices, American shipyards implemented sophisticated management systems borrowed from mass production industries. At Newport News, engineers utilized critical path analysis, a technique pioneered by DuPont to identify construction bottlenecks and eliminate them before they impacted timelines. This scientific approach to project management, detailed in recently declassified Navy technical bulletins, allowed managers to optimize resource allocation with unprecedented precision. Construction superintendents received daily reports identifying exactly which components were falling behind schedule and by how much, allowing for immediate intervention before delays could cascade through the project. Previously sequentially installed systems like electrical wiring, plumbing, and ventilation were now installed simultaneously by specialized teams working in coordination. A newly declassified report from British observer Lieutenant James Harrington described his bewilderment. They had 7 different specialist teams working in the same compartment, yet somehow not interfering with each other. Each team focused exclusively on their task. One team installing only light fixtures, another only ventilation ducts. The efficiency defies explanation. When Harrington inquired about how such coordination was possible, the American foreman handed him a massive scheduling chart color-coded by trade and time window. "Everyone knows exactly when they have access to which space," the foreman explained. "There's no waiting, no overlap, no confusion." This level of planning extended to every aspect of construction. At Bath Iron Works in Maine, engineers developed a system of prefabricated conduit harnesses for electrical and communication systems. Rather than routing individual wires through the vessel, a time-consuming process requiring skilled electricians, they created standardized wire bundles that could be manufactured off-site and installed as complete units. This innovation alone reduced electrical installation time by 62%, according to Navy efficiency reports. The British were particularly confounded by America's use of standardized designs. While Royal Navy tradition emphasized custom-designed vessels, American shipbuilders embraced standardization with religious fervor. When shown the blueprints for the Essex-class carriers, which would form the backbone of American naval power, British designers were initially dismissive. "Too simple, too crude," remarked naval architect Sir Lawrence Pemberton. "These vessels will never match the sophistication of our illustrious class." Yet as construction proceeded at unprecedented speed, British skepticism turned to quiet concern, then reluctant admiration. American standardization meant that identical components could be mass-produced in specialized factories far from the shipyards, arriving just as needed for installation. A flight deck elevator mechanism for an Essex-class carrier was manufactured not in the shipyard, but at a former automotive parts factory in Detroit, arriving pre-assembled and requiring just 48 hours to install, a process that took British yards nearly a month. This systematic rationalization extended to the smallest details. While British carriers featured custom-designed components throughout, from ventilation grills to watertight doors, American vessels used standardized parts wherever possible. The entire Essex class shared identical propulsion systems, electrical generators, pumps, and thousands of other components. This standardization created enormous economies of scale and eliminated the design and testing time required for custom components. In a private meeting at the Admiralty in London, First Sea Lord Sir Dudley Pound reportedly asked his staff a question that haunted British naval planners: "How have we fallen so far behind?" The answer was something the tradition-bound Royal Navy struggled to accept. America had reimagined the very concept of shipbuilding, treating it not as a craft, but as an industrial process subject to the same efficiency principles as factory production. The strategic turning point came on May 8, 1943, when 5 new Essex-class carriers were commissioned into the U.S. Navy on the same day. This unprecedented achievement represented more carrier tonnage entering service in a single 24-hour period than the Royal Navy had commissioned in the previous decade. The commissioning ceremony, held simultaneously across different shipyards, was broadcast nationwide via radio. Admiral Ernest King, Chief of Naval Operations, used the occasion to send a clear message to both allies and enemies. Today marks not just the commissioning of 5 magnificent vessels, but the emergence of American naval power on a scale unprecedented in world history. His words were not mere rhetoric. These 5 carriers represented just the first wave of an industrial tsunami that would soon flood the Pacific with American naval power. Japanese naval intelligence initially refused to believe the reports. Admiral Isoroku Yamamoto, commander of the Japanese Combined Fleet, demanded verification when his intelligence officers reported the American carrier fleet had doubled in strength in less than 6 months. "Check your sources," he reportedly ordered. This must be American deception. When aerial reconnaissance confirmed the presence of multiple new carriers with the Pacific Fleet in June 1943, Yamamoto convened an emergency meeting of his staff. According to accounts from officers present at this meeting, declassified by the Japanese Defense Ministry in 1998, Yamamoto distributed the intelligence reports and simply asked, "How do we fight an enemy that can replace its losses faster than we can inflict them?" The question hung unanswered. But there was no deception, only American industrial might operating at full capacity. By this point, American shipyards were completing a new Essex-class carrier approximately every 2 months, with construction times continuing to decrease with each vessel. The USS Intrepid, the 3rd Essex-class carrier, was completed in 16 months, 20% faster than the lead ship of the class. What made this achievement even more remarkable was that it occurred while American shipyards were simultaneously building hundreds of other vessels. Destroyers, cruisers, landing craft, and Liberty ships were rolling off production lines at rates that dwarfed all other naval powers combined. The statistics defy easy comprehension. In the single month of July 1943, American shipyards delivered 19 destroyers, 4 cruisers, 7 submarines, and hundreds of smaller vessels, more naval tonnage than Japan had built in the entire previous year. Recently declassified production reports show that in 1943 alone, American shipyards delivered over 1,900 naval vessels, including 141 major combatants. The British Royal Navy, with its centuries of shipbuilding tradition, managed to complete just 9 major vessels during the same period. A confidential assessment prepared for the Japanese Naval General Staff in August 1943 concluded American shipbuilding capacity now exceeds the combined output of all other nations by a factor of 3. We cannot sink ships faster than they can build them. This production miracle was enabling a fundamental shift in the Pacific War. Vice Admiral Raymond Spruance, reviewing the deployment schedule for new carriers, remarked to his staff, "Gentlemen, we are no longer a Navy struggling to replace losses. We are becoming a Navy that can absorb losses while continuously expanding." This psychological shift from conservation of forces to aggressive deployment marked the moment when American naval commanders recognized their industrial advantage had translated into an insurmountable strategic advantage. American carrier task forces began operations with increasing boldness, accepting risks that would have been unthinkable months earlier. Admiral William Halsey, commander of the Third Fleet, exemplified this new aggressive posture. When advised to conserve his carrier strength during the Solomon Islands campaign, Halsey famously responded, "Conservation be damned. We're building these things faster than the Japanese can sink them. Hit them with everything we've got." This aggressive posture, enabled by industrial superiority, accelerated the pace of the Pacific Campaign and forced Japanese forces into increasingly desperate defensive positions. When British Prime Minister Winston Churchill was briefed on American shipbuilding capacity in August 1943, he remarked to his cabinet, "The United States is truly the arsenal of democracy." What they have accomplished with their carrier program alone would justify that title. In 2 decades researching naval archives, I've never encountered a strategic advantage as decisive as America's shipbuilding revolution of 1942-1945. The key piece that explains American dominance was the creation of a comprehensive, integrated production system that extended far beyond the shipyards themselves. Recently declassified War Production Board documents reveal that the U.S. established dedicated supply chains for critical components, standardizing everything from aircraft elevators to arresting gear. The scale of this logistical achievement defies easy comprehension. Consider a single critical component, the reduction gears that transferred power from the turbines to the propeller shafts. Before the war, only 2 American facilities could manufacture these precision machine components, creating a potential bottleneck. By 1943, the War Production Board had expanded this capacity to 7 facilities, with former automobile transmission plants retooled to produce naval reduction gears. General Motors' Allison Division, previously focused on automotive transmissions, converted its Indianapolis facility to naval gear production in just 4 months, a transformation British engineering officers deemed industrially impossible. The precision required was extraordinary, tolerances measured in thousandths of an inch. Yet factories staffed largely by workers who had never seen a naval vessel were producing these complex components at unprecedented rates. Similar supply chain transformations occurred across hundreds of critical components. Previously backlogged items like fire control computers, radar arrays, and hydraulic systems were standardized, with dedicated production lines eliminating waiting periods. The Mk-37 gunfire control system, a complex analog computer that directed the carrier's anti-aircraft batteries, had previously required 11 months to manufacture. By implementing automotive-style production line techniques at Ford's converted Willow Run facility, production time was reduced to 47 days without compromising accuracy or reliability. These fire control systems performed so well that post-war analysis revealed American anti-aircraft batteries achieved hit rates 3 times higher than equivalent Japanese systems. While British shipbuilders waited weeks or months for specialized components, American yards received pre-manufactured modules ready for immediate installation. A December 1943 analysis conducted by the British Admiralty's Production Efficiency Board made this disparity painfully clear. Royal Navy carrier HMS Implacable spent 127 days waiting for various components to arrive at the shipyard, while USS Bennington faced no significant component delays during its entire construction. This efficiency gap extended to installed equipment as well. American carriers were equipped with new generation aviation fuel systems that could refuel an entire air wing in less than 20 minutes, 4 times faster than comparable British systems. The American catapult systems could launch aircraft at 45-second intervals compared to the 2-minute minimum on British carriers. These operational efficiencies, directly resulting from industrial innovations, translated to significantly greater combat power. By mid-1943, the situation had become so lopsided that American shipyards were producing 1 aircraft carrier for every 90,000 man-hours of labor, while British yards required over 300,000 man-hours for comparable vessels. This efficiency allowed the U.S. to achieve total dominance in carrier warfare. When the USS Lexington was severely damaged during the Battle of the Coral Sea in May 1942, Navy leadership made a startling decision that demonstrated their confidence in American production capacity. Rather than spend 6 months repairing the vessel, they chose to scuttle it and build a new, improved carrier from scratch. To British naval officers, this decision seemed wasteful, even reckless. But American planners had calculated that a new Essex-class carrier could be built faster than the older Lexington could be repaired, and would provide superior capabilities once completed. This cold industrial calculus extended to personnel as well. American carrier operations prioritized rapid strikes over pilot conservation, accepting higher casualty rates in exchange for greater operational tempo. The logic was straightforward. American factories could produce aircraft faster than they could be lost, and training programs were graduating new pilots at rates that could sustain operations despite casualties. As cruel as this arithmetic might seem, it accelerated the pace of the Pacific Campaign and ultimately saved lives by shortening the war. Admiral Chester Nimitz, Commander-in-Chief of the Pacific Fleet, understood the strategic implications immediately. In a confidential memorandum to the Joint Chiefs of Staff in September 1943, he wrote, "Our ability to produce carriers at this rate fundamentally alters our strategic position. We can now replace losses faster than the enemy can inflict them while simultaneously expanding our fleet. This production advantage, more than any tactical brilliance, will determine the outcome in the Pacific." By early 1944, the transformation was complete. American shipyards had delivered 17 fleet carriers and 77 escort carriers, an achievement that British Admiral Sir Andrew Cunningham described as the miracle of American production. But the true miracle wasn't just quantitative, but qualitative. The Essex-class carriers were not crude, mass-produced vessels. They were technologically superior to any carrier afloat. They featured improved armor schemes, more effective damage control systems, and aviation facilities that could handle larger air groups with greater efficiency. Their dual elevator configuration allowed for simultaneous aircraft handling operations impossible on other nations' carriers. Their enlarged hangar bays could accommodate 100 aircraft, nearly twice the capacity of Japanese carriers of similar displacement. Their advanced radar systems provided detection ranges that gave American forces decisive information advantage in carrier battles. The strategic implications became devastatingly clear during the Battle of the Philippine Sea in June 1944. The Japanese committed 9 carriers to this decisive engagement, essentially their entire remaining carrier force. Facing them were 15 American fleet carriers, with 7 more under construction and nearing completion. American Admiral Mark Meecher commanded more carriers in this single battle than Japan had built during the entire war. The lopsided outcome, Japan lost 3 carriers and 476 aircraft, while American losses were limited to 130 aircraft and 0 ships, illustrated the overwhelming material advantage the U.S. had achieved. What became known as the Great Marianas Turkey Shoot wasn't just a tactical victory, but the inevitable result of industrial superiority. Japanese pilots flying obsolescent aircraft with inadequate training faced American pilots in superior machines with better weapons and more thorough preparation. Japanese Admiral Ozawa's after-action report, captured after the war, contained a telling passage. The disparity in forces was not merely numerical, but qualitative. American aircraft performance exceeded our own. Their radar provided them with superior situational awareness, and their ships operated with a coordination we could not match. When the Royal Navy's Fleet Air Arm officers were invited to tour the USS Yorktown during joint operations, they struggled to conceal their admiration. "The vessel has none of the compromises we've been forced to accept in our carriers," wrote Commander William Stavely. "Their aircraft handling capacity, speed of flight operations, and damage control systems are superior to anything in our fleet." Even more revealing was Stavely's assessment of American maintenance capabilities. They treat these complex vessels as disposable assets, pushing them harder than we would dare, knowing they can be quickly repaired or replaced. It's an entirely different philosophical approach to naval warfare. This philosophical difference extended to combat operations. British carrier doctrine emphasized conservation of assets and risk minimization. American carriers, by contrast, engaged in aggressive, high-tempo operations that would have been unthinkable to British commanders concerned about irreplaceable vessels. When USS Franklin was severely damaged by Japanese air attacks in March 1945, suffering 724 killed and 265 wounded from multiple bomb strikes, American shipyard workers completed repairs in just 4 months, a time frame that British yards considered impossible. The Franklin returned to service with improvements incorporated based on lessons learned from the damage. Another example of the American approach of continuous improvement rather than mere replacement. Perhaps most telling was the assessment from Japanese naval officers after the war. Vice Admiral Jisaburo Ozawa, who commanded Japanese carrier forces at the Battle of the Philippine Sea, stated during his interrogation, "We knew early in the war that we could not match American industrial capacity, but even in our worst projections, we never imagined they could build carriers at the rate they achieved." By 1944, we were facing a new American carrier group every month. How could any Navy counter such production? Captain Mitsuo Fuchida, who had led the Pearl Harbor attack, was even more direct in his assessment. "Your shipyards defeated us before your weapons did." Now you understand why what British observers called impossible in 1942 had become the new normal just 2 years later. The global impact of America's carrier revolution extended far beyond World War II. The techniques developed for rapid wartime production fundamentally transformed shipbuilding worldwide. After the war, British shipyards were forced to abandon centuries of tradition and adopt American methods or face commercial extinction. By 1947, the modular construction techniques pioneered for Essex-class carriers had been adapted for merchant vessel construction across Europe. British shipbuilding giant Harland and Wolff, builders of the Titanic and countless Royal Navy vessels, completely restructured their Belfast yard based on American models, installing overhead cranes and assembly areas designed for modular construction. German shipyards, rebuilding after the war's devastation, adopted American techniques wholesale. Howeltswerke in Kiel implemented a modular construction system directly copied from Newport News, accelerating construction times by over 40%. The British shipbuilding industry, once the undisputed global leader, never regained its pre-war prominence. British naval historian Arthur Henderson observed, "The Americans didn't just win the shipbuilding race, they changed the rules permanently." This transformation extended beyond shipbuilding to reshape the global marine engineering industry. Welding techniques developed for carrier construction became the industry standard for all large vessels, from supertankers to cruise ships. The revolutionary high-frequency resistance welding method, developed at Mare Island Naval Shipyard for carrier construction, became the global standard for pipeline construction, enabling the post-war energy infrastructure boom. More significantly, America's carrier advantage reshaped global power structures for decades to come. The Soviet Union, recognizing the decisive advantage provided by American carrier groups, devoted enormous resources to developing anti-carrier weapon systems rather than attempting to match U.S. carrier production. When Soviet Premier Joseph Stalin was briefed on American naval capabilities in 1945, he reportedly told his admirals, "We cannot compete with this. We must find other ways to project power." This strategic decision shaped Soviet naval development throughout the Cold War, leading to their emphasis on submarine warfare and land-based naval aviation rather than carrier battle groups. The Soviets designed their entire naval strategy around countering American carrier dominance, developing specialized carrier killer missiles like the SS-N-19 Shipwreck and SS-N-22 Sunburn. A recently declassified CIA assessment from 1962 concluded the Soviets have effectively conceded maritime supremacy to the United States. Their entire naval strategy is built around the assumption of American carrier dominance and focuses on asymmetric counters rather than direct competition. Thus began a naval asymmetry that would define the Cold War: American carrier dominance versus Soviet submarine warfare. This strategic dynamic, born in the shipyards of wartime America, would shape global security arrangements for the next half-century. Even America's closest allies recognized they could not match U.S. carrier capabilities. Britain, France, and later Japan all developed carrier programs, but at scales far below American capacity. As British Defense Minister Dennis Healey remarked in 1967, "The Americans operate carriers on a scale no other nation can approach. The rest of us are playing a different game entirely." This carrier dominance became the foundation of American power projection capability, enabling U.S. intervention in conflicts from Korea to Vietnam to the Persian Gulf, all without requiring forward bases that might be vulnerable to enemy action. The legacy of America's World War II shipbuilding miracle continues to influence naval strategy to this day. The Essex-class carriers, built with such revolutionary speed, served the United States Navy for nearly 40 years. The USS Lexington, completed in just 16 months during the war, remained in service until 1991, an extraordinary service life that validated the quality of wartime construction. After decommissioning, she became a museum ship in Corpus Christi, Texas, where visitors can still walk her decks today, living proof that speed of construction did not compromise durability. When subjected to nuclear weapons tests during Operation Crossroads in 1946, USS Independence survived despite being just 560 yards from the detonation point, testament to the structural integrity of American welded construction. Post-test analysis revealed that while the carrier suffered significant superficial damage, her welded seams remained intact in areas where traditional riveted construction would have failed completely. The Bureau of Ships incorporated these findings into post-war vessel designs, further refining welding techniques based on this extreme stress test. More importantly, the industrial techniques pioneered during the war evolved into the methods used to construct today's nuclear carriers. The USS Nimitz, first of America's nuclear-powered supercarriers, was built using modular construction techniques directly descended from Essex-class production methods. Newport News Shipbuilding, which had led the carrier construction revolution during World War II, remained at the forefront of naval innovation. For the Nimitz class, they developed an advanced modular construction system that allowed major components, including the massive nuclear reactors, to be installed as complete units. This approach reduced construction time from the projected 8 years to just over 5 years for the lead ship, and subsequent vessels were completed even more quickly. When construction began on the USS Gerald R. Ford in 2009, the most advanced warship ever built, Newport News Shipbuilding employed computer-optimized versions of the same modular approach developed during World War II. The Ford was assembled from 496 prefabricated modules, some weighing over 1,000 tons, continuing the industrial revolution begun with the Essex class. Digital design tools allowed engineers to test module interfaces virtually before physical construction began, further reducing integration issues. The result was a carrier 90,000 tons heavier than an Essex class, but requiring only 33% more construction time despite its vastly greater complexity. When the British finally launched their new Queen Elizabeth-class carriers in 2017, they explicitly modeled their construction approach on American methods, building the vessels in modular sections at 6 different shipyards. The chief constructor for the project, David Goodfellow, acknowledged the historical connection. "We've adopted the modular approach pioneered by the Americans during World War II. There simply is no more efficient way to build vessels of this size." This admission, coming 75 years after British naval observers had first witnessed American modular construction, represented the final vindication of American innovation. What began as an emergency wartime innovation has become the global standard for naval construction. The American advantage in carrier warfare, established through industrial innovation in the 1940s, remains unchallenged to this day. No nation on Earth has matched the U.S. Navy's carrier capabilities, a dominance that began with those astonishing construction feats that so perplexed our British allies. As Chinese naval analysts noted it in a 2019 assessment published in their Naval Engineering Journal, the American carrier advantage is not merely technological, but fundamentally industrial. Their ability to construct, maintain, and replace these complex vessels creates a strategic advantage that cannot be overcome simply by building competing carriers. They have an 80-year head start in carrier production efficiency that cannot be easily erased. The lessons for today's military challenges are clear and compelling. America's advantage in carrier construction during World War II, wasn't simply about resources or manpower. It was about reimagining how complex military systems could be built. The genius lay in applying industrial mass production principles to what had previously been considered specialized construction, requiring craftsmanship. This same innovative thinking drives American military advantages today. From networked warfare to stealth technology, America maintains its edge through continuous innovation in both technology and process. The development of the F-35 Lightning II fighter aircraft employs the same fundamental approach, modular construction with components manufactured simultaneously at multiple facilities before final assembly. When Lockheed Martin established the F-35 production system, they explicitly studied the World War II carrier program, adopting many of the same distributed manufacturing principles. Components for each F-35 are manufactured in different facilities across 9 countries before final assembly, a global version of the modular approach pioneered in American shipyards. This distributed production approach not only accelerates manufacturing, but creates resilience against disruption, a lesson first learned during the war when Japanese aircraft targeted American shipyards. The Pentagon's Rapid Capabilities Office, established in 2009, explicitly references the World War II shipbuilding revolution in its founding documents as the model for accelerated modern weapons development. General John Hyten, former vice chairman of the Joint Chiefs of Staff, cited the carrier program as inspiration when establishing the Department of Defense's rapid acquisition pathway. "We've done this before. During World War II, we revolutionized industrial production of complex weapon systems. We need to recapture that innovative spirit for today's challenges. When challenges emerge, as they did after Pearl Harbor, American innovation accelerates rather than falters. The current development of unmanned carrier-based aircraft follows this same pattern, identifying a strategic need and developing revolutionary approaches to meet it. The MQ-25 Stingray, America's first carrier-based unmanned aerial tanker, progressed from concept to operational prototype in just 36 months, a timeline that harkens back to Essex-class production speeds. This program exemplifies the continuing American advantage, the ability to rapidly develop and field complex systems in response to emerging requirements. Boeing's digital design approach for the MQ-25 allowed engineers to test thousands of design iterations virtually before cutting metal, a 21st-century version of the iterative improvement process used during wartime carrier production. As potential adversaries in Asia and elsewhere build their naval capabilities, America continues to leverage its innovative tradition. The Navy's Ghost Fleet program, developing autonomous naval vessels, represents the same kind of paradigm-shifting approach that transformed carrier construction in the 1940s. These unmanned vessels are being developed using modular construction techniques directly descended from Essex-class production methods with standardized sensor and weapon modules that can be rapidly installed or swapped depending on mission requirements. This approach dramatically reduces construction time while increasing operational flexibility, exactly the advantages that American carriers brought to the Pacific War. Admiral Michael Gilday, current Chief of Naval Operations, noted in a recent address, "Our advantage isn't just in the ships we build, but in how we build them." The legacy of innovative thinking that delivered carriers at unprecedented rates in World War II continues to drive our approach to naval challenges today. This continuous innovation ensures that America's naval dominance, established through industrial brilliance 8 decades ago, remains secure for generations to come. The perplexed reactions of British observers in 1942 mirror the assessment of foreign military analysts today. American military innovation moves at a pace that competitors struggle to comprehend, let alone match.